All right. So we just heard 4 talks. These talks covered the theory and experiments, and I like how the experimenters have interspersed themselves between theorists, which is a fantastic way of arranging. As somebody who has done significant amount of work in theory and then tried to varying degrees of success implement this work in experiments, I appreciate all the viewpoints here. I think that just like we did with other panels, let's first have the panelists briefly reintroduce themselves. And the first question that I'm going to ask is, so we have seen the work on theory, and some people claim that theory is easy to do. Those people usually are the ones who do experiments. And then we also have seen work on experiments, and some people claim that experiments are way more productive and get you more money, and those people are usually the theorists. Now, the problem, I think, is that we need a bridge between the two. We need actually theorists talking to experimentalists, and making sure that their theories don't stray too far from the actual reality, while experimentalists are actually doing interesting work rather than making up the problems to solve with measurements as they go. So let's reintroduce ourselves, and maybe after brief introductions, start addressing that question, whoever wants to go first, right? So go ahead.
Okay, yeah, Thomas Kürner. I'm here from the Institute, here leading the Mobile Radio Systems group, and one of the tasks, not the only task I'm doing, is working on terahertz communications for more than 20 years right now, both with simulation, but also with a lot of measurements. Should I address the question right now, or first do the introduction? How do you think?
I mean, we can start addressing it right now. So I think that's a good idea. Yeah.
I don't know how you wanted to to have. Yes, I think that is really a key issue, bringing the two worlds together. Of course, it doesn't make a lot of sense to make only theory without having the link to the realization, because there is a lot of things that just cannot be built, what you think, what might work in theory. And on the other hand, if you talk to people that are just doing the experiments, yeah, sometimes they are then doing things when they think, okay, think a little bit and ask the people from the theory. This could help. So I really appreciate to have both worlds, and I'm in many projects where there is representatives from both sides. And I like it especially since it's not only the bridge theory to experiment. So I'm now in the Institute for Communications Engineering, but originally I'm from microwave engineering. So I'm the microwave engineer within the communications engineering. When I did my PhD, it was just the other way around. I was in the microwave engineering thing and doing things related to communications engineering. Also there, it is also important to talk to each other, because the communications engineering people, they tend to write something down. Everything is ideal. All the systems are behaving ideal, but they don't. And so it's the microwave engineers that have to build things based on what the communications engineering people say, but also the communications engineering people have to take into account what's feasible and yes, what's not. So therefore, this interdisciplinary things between different disciplines, but also between experiments and theory, this is important. And this is the things that will bring things forward.
Yes.
So maybe now I have talked
very good
a lot.
So introduce yourself again, and then give your perspective on. And also, this I should have said that the panel is supposed to focus on challenging topics in terahertz, VLC, FSO, and non-terrestrial networking. I think that the question I ask applies to all of them, which is why I asked it. But of course, definitely feel free to bring in your own expertise in those particular fields. So yes, please go ahead. Sorry.
Okay, thank you. Yes, I'm Mahtab Mirmohseni, and I'm an associate professor at Institute for Communication Systems, University of Surrey. And my research interests are mainly in the theory side, in information theory, and also in security and privacy communication. But in University of Surrey, in Institute for Communication Systems, we have a test bed team. And we have people who are dedicated to do experiments in 5G. And though I do not run the experiments myself, I have the opportunity to collaborate with them. And in most of the, let's say, proposals, projects, we have a work package which is dedicated to use the result of the theory in the with the testbed team, and they can apply those. We are developing that, let's say, because as you said, there is a big gap between our results in the information theory side, especially. Okay, the communication theory is much more easier to be adapted in experiments, let's say, but the information theoretical results is hard, especially for the channel part, because it needs a lot of changes in the physical layer side. It can be the findings which can be applied at the application layer, which are related to the source coding part, or even the coding theory part, is easier to be adapted to some applications. But the channel coding part, which needs extensive modification in the physical layer, it's not that easy to do. But if we combine them with some communication theory, like beamforming, or even some finding that we can apply in our test bed, we try to do that, at least. Yes, I know that it's really hard even for the theory people to understand the difficulties of and the challenges of the practical and the experimental side. But from our point of view, I should say that if experimental people just tell to us that these are the main bottlenecks, main challenges, and we will be happy to somehow model that or consider those bottlenecks in our abstract models or whatever we have to find some solutions to make these two sides, get closer, actually. Thank you.
Surrey, that's Guildford?
Yeah.
Yeah. I was in Guildford last year.
Yeah.
Yeah. Sorry. Let's continue later. Okay. My name is Stephan Brink from University of Stuttgart, and thanks for having me on the panel. How do I relate to practice and theory? I was active in standardization, in Wi-Fi standardization 2003, 2010, and that is where theory and reality, I don't want to say crash together, but you see a lot of new things happening there. Maybe some of you know the 50-60 hertz flicker noise in the Wi-Fi channel model. That came out of measurements, and that came out of issues that people had with their chips. So they built chips, and the chips had issues because of fluorescent lights.
Oh, yeah.
And a lot of much more fluorescent lights than this, maybe. And they are actually reflectors. Hey, RIS, that was the RIS of 2005.
Yes, uncontrolled
so
RIS.
whenever they are on, they reflect, and when they are off, they don't reflect. So these chips had weird receive patterns, and no one understood this to begin with. And then later they figured out, oh my God, it's this mirror on the ceiling, and that then went to the model, and then the theorists or the communications engineers. It's of course a seamless I don't want to see there's one theory guy, there's one the practice guy. It's people. Some people are both, hopefully. Then they were able to put this into their algorithms and to consider and how to mitigate those effects. So I think from measurements we have a lot of important insight feeding back into theory and the other way around. For example, just to wrap this up, MIMO capacity, Emre Telatar and Jerry Foschini, they came up with this. Jerry Foschini was more practical guy, and Emre Telatar is an die-hard information theory guy, right? And these MIMO capacity equations are so useful because when you do measurements, you can always benchmark the capacity that you get the CSI values, you can compute determinants, you can compute capacities, and you will see that as you increase the number of antennas in this room, it will saturate, flatten out, whereas the IID complex Gaussian ergodic thing will continue like this. So theory provides the limits of communications and makes measurements plausible. If you're beyond that, from your measurements, something is wrong. If you're below that, you can always explain this by, hey, we don't have a perfectly scattering channel, for example, in the MIMO case. So, very important. Thank you.
Okay. I'm Karl-Ludwig Besser. I'm an assistant professor at Linköping University in Sweden in the Division of Communication Systems. And my work focuses mostly on resilience, ultra-reliable communications, physical layer security, and is theoretical, I would say purely theoretical, and also the whole division. Okay. Our division doesn't even have, I think, any hardware where we could test the things we come up with. So from my perspective, I mean, of course it is important to have both, and I think much has been said already that you have this convergence, and the hardware people will hopefully provide you some boundaries, so to speak. And what I think is important nowadays, and I don't know if any of you have read that, but Robert Heath you recently used this word assumption slop to describe like many theoretical papers nowadays. They just make assumptions for the sake of it, to kind of like, oh, now I have a new optimization problem which I can solve, and like all these assumptions are just kind of like slop, just random assumption which makes the theory look nice, but there's no, like, if you give this to an experimentalist, they would say like, okay, that's like this assumption not even in kind of an idealized system makes sense. So I think it's especially important to avoid this kind of thing. I think it's fine for theory to idealize some parts, because sometimes you maybe only want to focus on specific aspects, specific effects in your system, and if you consider everything to be imperfect, then it's just like unfeasible, or you cannot really solve this. But I think it's important to keep in mind what are like real, like what assumptions are valuable. Yeah. Okay, thank you.
Very good. Now, you mentioned that you, I'm talking to Professor Mirmohseni here, you mentioned that you include the the experimental work in work packages in your theory proposals. That's fantastic. Could you kind of elaborate what your experiences were? Clearly you won some of those proposals. So how did that all work out? Did the theorists kind of sit in their own room making assumptions that are, I don't want to call it assumption slop. That's a bit derogatory, because we have AI slop, which is far worse than making an IID assumption, for instance. But let's say unreasonable assumptions, or maybe assumptions which are not completely driven by the system reality, and rather by the need to make the problem mathematically tractable. So, or was there actual meetings? Were there PhD students that wrote papers with each other? That's a great indicator of having a robust bridge between theorists. When PhD students collaborate on papers, you have theory PhD students and experimentalists working on a problem, and you see them in both papers. Have you had that experience, and what was it like? Is it more difficult, easier, both? My guess is more rewarding because I think that the funding agencies love that kind of stuff. But what is your opinion on that? Well, you can go. Yes. Yeah.
Okay, actually, that's a very good idea, but we haven't had that experience of having two PhD students working on that. We do actually in either two ways. I have some colleagues who do more practical works. They are people that just, for example, really building some RISs or something like that. And when we are trying to have discussions, actually we have now projects, and we are trying to make our models closer to what they are really building. For example, if we consider an array of some elements that we can control the phase of each element separately, they say that no, this is what we can do, that we can just switch between 10 phase shifts, and so we want just to make all them closer to what they think. This is one way that we work with the people who do experiments. Another one is the testbed team. Testbed team they have a testbed through our campus. They run 5G through our campus, and we work with them if we want access or we want to run some protocol, something new. Mostly now we do some security stuff on that because it's easier to affect, for example, AKA protocol and authentication and key agreement protocol in the 5G. If we are doing some changes in that protocol, and they can apply that and give us some real 5G data to see that what will happen. And this is how we do research with them. Having yes, two PhD students. Okay, for PhD students, maybe it's a bit more difficult because if we have a theory PhD student and very practical PhD student, it's maybe harder for them to work with each other, and they need someone to make that connection between them. So someone that knows the alphabet of, let's say, two area, and they can speak to each other using that. But yeah, maybe we can also think of that. Thank you for the.
Yes. All right, does anybody else want to say something on that regard? Thank you.
I have one scary example of not taking reality into account. Like, and everybody can relate to this. So you guys do simulations, and you simulate all sorts of stuff. For example, frequency offset. Frequency offset between transmitter and receiver. Okay? And there was a time I even built chips that compensate for this. And that the problem is that in a real receiver, the frequency offset is due to the mismatch of the crystal, and that takes the carrier frequency to a different frequency, and the sampling clock. It's the same. So I would claim 80% of average PhD students, they only consider the carrier frequency shift, but since they are so into simulating discrete time systems, they forget about that also the discrete time base is skewed. And let me tell you, in many systems that doesn't matter, because this timing skew is so little over a packet, Wi-Fi, it won't hurt. But as soon as you have an ultra-wideband system, it hurts. The subcarriers drift away in different rotations. And just to wrap up this funny story, because I think it's a funny story. So we built a chip that didn't do this. It was a test chip. So we went to a Wi-Fi certification event for 40 megahertz, from 20 to 40 megahertz. And we figured, oh man, it doesn't work well. And realized the problem. And then our hardware guy put in different crystals, like there's plus minus 20 ppm, and he had like 10 different crystals that he measured. Okay, that has 5, that has 8, and then depending on which device we were talking to, he switched.
Wow.
And then we got certified with a chip that wasn't fit. Of course, the chip that then went to the market was fixed. But hey, as a PhD student coming out of a university, you think you own this system, you understand everything. I missed that, right? And luckily, it was not 500 million that was lost, but it was captured by measurements, by real life interactions. It's a total stupid thing, right? And once you are aware of that, you will never forget about this. But that shows you that sometimes you have implicit assumptions about a system that are not true. In a wireless radio, the sampling clock and the carrier frequency is derived from the same crystal. It's different in optical. In optical, the carrier frequency is the laser, and that drifts away like crazy, and the crystal, the clock is separate. So all of these things, implicit assumptions, they may be wrong, or they may be right, and only measurement shows what's the real thing is.
Measurement and careful tracing of the transmit-receive chain, because
it shows you where you got wrong.
Yes.
And there's nothing to debate.
Yes.
I can add a similar story where we have seen that you can also overdo if you are with a theory. You are in a project, and there were people working on theory, the channel measurement guys, were we, and there was also a group doing the RF hardware. It was about 300 gigahertz, and the discussion was about, do we have to consider near field effects or not? And so the theory people, they told us, yeah, you have to consider the near field model, and this would have made things quite complicated if we cannot do the calculations based on far field. And there was a lot of discussion. Yeah, there is a paper that shows that there is an effect. The paper was on archive, and during the discussion I downloaded a theory paper. I downloaded the paper, and I looked to the paper, and I said, okay, yes, there is a difference. Over the whole antenna array, there is a difference of 1 dB. And then I thought, okay, channel measurement guys, 1 dB, we don't care, we cannot measure that accurate. And behind me were the people who designed the RF hardware, were sitting and said, can you design your hardware so that your transmit power is accurate within 1 dB? I said, no. I said, okay, problem solved, we don't have to consider this.
I have a similar story, like a pleasant surprise that happened in practice. Is I complained about how much data the software-defined radios generate. You're very familiar with that, having all those SD drives. Well, it's great because we can actually use the central limit theorem, and it converges fairly nicely. You have all the shapes that you need. So sometimes in practice things actually work out, like what you said. But it is important to actually step through and make sure, because if the difference was 30 dB, then you'd have a problem. Yes.
Exactly. I didn't want to say, okay, it's useless to look on the theory, but at some point you have to match.
So that goes to another. So there was, I think that there was a talk, and one of the problems they faced was inversion matrix. I don't think this person on a panel, unfortunately, but I may. Oh, yes. So there are all these matrix inversion problems that happen when you try to use these massive MIMOs and constrain them by security and other considerations, and somehow our phones still work. And there's MIMO in here. There's multiple antennas. If you pull this apart, they're going to find them. And so clearly, engineers know how to deal with these problems, and those who make these phones know how to deal with these problems. No quantum computing is necessary, by the way, I can tell you that, for that particular problem. But it's so how much, we're here at this workshop. It's sponsored by DFG, which is the German equivalent of the National Science Foundation, very fundamental. There's also Siemens who is sponsoring some, so Siemens is not fundamental. They care about actually building devices. I mean, how do we make academic research be compatible with what's out there, which is these things, and actually being useful for further improvement, besides producing brilliant students who go on to careers in these companies and make them more profitable and make the world better as a result. So I don't know, maybe you can talk about your experience in the theoretical world and how you whether you had students who went on and decided to go and try the industry thing.
Sure. Maybe the question could also be, or you could ask kind of the opposite question, does it have to be like that? Do academia and industry need to kind of converge? Maybe it is also fine that academia is looking at different problems, maybe is kind of, in that sense, far ahead and talks about problems which are not, or ideas which are maybe not implementable yet. But maybe they are in 10 years, 20 years. And you already said that. I guess it's a major contribution of academia also to just educate people and to have brilliant people who then go into industry and actually make the progress and make things happen in the real world, so to speak. So I'm not sure if it's necessary to basically enforce academia and industry to kind of work on, in that sense, the same problems.
Well, not the same problems, of course.
No, but even like conceptually, that you could say, okay, it's also fine if academia considers things, problems, ideas which are too far from reality yet. But maybe hopefully they become reality at one point rather sooner than later.
Do you want to respond to that? Yes.
Yeah. There is a very famous example on that. So I also have to do the channel coding lecture in Braunschweig, and it's the LDPC codes.
Yes.
They have been invented in the 60s, but at that time it was absolutely no chance to implement them. So from an industry perspective, at that point of view, it was useless because you cannot implement. It was a pure academic exercise. 40 years later or 50 years later, signal processing technology was that advanced that it was possible, and nowadays is there. So sometimes these basic research things, even if it looks this is crazy, useless stuff, it may materialize a couple of years or even decades later, and therefore we should do it. If we don't have these basic things, also for the implementable things, we will not make progress.
I completely agree. I'm a theorist, and I agree with both of you. I think that, you go ahead.
Actually, I chip in on this. Same was for MIMO technology, like was in 1995, and the service providers, Verizon and all those guys in the US, they said, way too expensive, we do sectorization, and we don't need this MIMO stuff, right? Way too expensive. And the first guys to put this into reality were the Wi-Fi guys, because the Wi-Fi guys, like IEEE 802.11, they were like cowboys, like cowboys and cowgirls. they don't care. They put everything that's new, like LDPC code's the same thing, by the way. They put everything in there and mix it up, and then let the market decide what prevails. Like. And hey, 802.11n was a great success because higher data rates and more spatial reuse. And LDPC codes, I guess, at some point in time they were also used. They were all in there as options, not as mandatory modes of operation. And it's a pretty cool thing. Like 3GPP, 5G, 6G is a bit different. But it's true. I mean, the theoretical understanding of MIMO was in the 90s. The first widespread use was 2006, 7, 8 in 802.11. So it's 10 years. So maybe the same happens for RIS. We don't know. I agree. So what I'm saying is I agree. Yeah. Theory always is way ahead, and if some of the things never show up in reality, okay, for other reasons. Relays never really showed up in reality because it's much more expensive to rent this physical space to put the base station there. So if you have a cheaper base station being a relay, the cost of renting the space is so much more that they just put in base station. So not for technical reasons. So, yeah.
Does the audience have any questions? I kind of have been the one who was asking them, but would love participation. Anybody have anything that they would like to contribute here? Question, comment, thought? So let's thank the panelists and let's enjoy our conversation and Mensa, right?